So yesterday, we had finished with this slide. I had gone through a little derivation to give us the relationship between Kc and Kp. Two different ways to determine an equilibrium constant depending on what information you're given. If you're given pressures of gases, we would find Kp. If you're given concentrations, we find Kc. But if for some reason you needed one of the K's but you have the other, then we can get from one to the other using this. And I derived that from the ideal gas law. That's why the R and T are doing there. Now, before we go and take a look at a couple of examples using this formula, I do want to remind you of what I had written down here on the bottom of this. The R value in here, we have kind of conditioned our brain. When we see an R in a formula, we automatically are tending to use 8.31. Because we've done so much with energy in the last couple of months, really starting at the beginning of November. So it's been a full couple of months that we were doing thermodynamics. And every R that we saw, we had the kilopascal times liter, remember, is a joule, which corresponds with the unit of energy. So we've been using 8.31 constantly. Do remember, though, there are two other values of R, and we use the ideal gas law. The R value depends on what the pressure unit is. I had mentioned this back in chapter 17, but we didn't really do anything with it. When you find Kp, that Kp must be the ratio of the pressures of gases in the unit atmospheres. And you'll see whenever we have a Kp problem here in chapter 13, it will always give you atmospheres as the pressure unit. They're not going to give you, I don't think they're going to give you kilopascals or torr. They'll give you atmospheres because it's the ratio of atmospheres, products over reactants. The R value that corresponds with atmospheres is 0.0821. So you must use that R value when you're using this, because that derivation came from the ideal gas law. So yeah, I just want to remind you of that. Let's go to now number 10 and number 11. So the next example we'll do number 10, and then the next one is number 11. So we'll just stay there on the that example doc. Okay, so number 10 is right here. Hopefully you're there too. Consider the hydrogen shift reaction. I don't really know why it calls it the hydrogen shift. It's more of an oxygen shift because the oxygen leaves the water and goes onto the CO. But anyway, they didn't ask me to name it. So they give you the Kc value for this reaction. And the question is, what is the Kp value at the same temperature? And by the way, I've had people asking today, will we ever have a problem where the temperature changes? If they give us Kc at one temperature, will they ask us for Kp at a different temperature? No, you're not going to have that. It'll always be at the same temperature. So we know Kc, we want to find Kp, so we're going to make use of our formula that we've learned. Kp equals Kc times RT raised to the delta N power. Now, I think I asked you this yesterday. When is it that Kp is equal to Kc? Do you remember? Did I ask you that? When is it that you?
It's when like the moles of gas in the products and the moles of gas in the reactants are the same.
That's right, yeah. If you have the same number of moles of gas on both sides. And look at what we have here in our good old hydrogen shift reaction. 2 moles of gas on the left, 2 moles of gas on the right. Easy problem. Kp is equal to Kc, and so since Kc was 1.873, we're going to choose A for the end. All right, so we'll start off with something ultra easy. Then we'll get, are we good with that? Does that make sense? We don't really have to do any calculation. We know that this exponent is 0, so therefore this whole term is 1, and we'll move on. Number 11. Now this one we will have to do a calculation for. I'm going to move this up. Oops. Because number 12 has this blank space. I'll do the math in the blank space. Number 11. Consider this reaction. The type on this didn't turn out very well. And they took, I don't know where it went to, but we've lost the plus sign between the two reactants. So it's CS2 plus 4H2. It's 5 particles of gas on the left. And yields CH4 plus 2H2S. So if we are given the equilibrium constant K is 28, do you remember I told you this yesterday? If you have an unspecified K, it just says K. Does that mean KC or KP? It's KC, right. And besides that, it says what is KP at this temperature, so you're going to have to find the other one. Yeah, but if you have an unspecified K, it does mean KC. So KC is 0.28, and therefore, what is KP at this temperature? I'm going to give you a moment, see if you can do this calculation, getting everything right. Here's the formula for it. Be careful, look what I put for the temperature. Did you put that too? Temperature has to be in Kelvin. Jay Sung, I'm on your side because I want to see him go bold. Okay, so we have this calculation. What's the multiple choice answer?
C.
It is C, yeah. And I want you to notice something. This is, I think, worth noting. The Kc value is 0.28. The Kp is 3 times 10 to the negative fifth. What a huge difference that is. It's a huge difference. So, yeah, notice that the difference between Kp and Kc is not a subtle difference necessarily. If you have a big high temperature, it's a big difference between those two things. Because, yeah, the concentration, if the pressure goes up, the concentration goes up as well. But that ratio of concentrations can be affected big time. And that exponent on there too, that makes a big difference. Okay, so we're going to now go back. Got something new now to teach you today about equilibrium. It's called an ice table. Now, when I say ice table, we all think of ice, frozen water. This is not anything to do with ice that we put in our drinks. An ice table is a means for keeping ourselves organized as we do equilibrium problems. This is where the math is going to get very heavy for us. You're going to have problems in which the problem will describe a reaction. It'll tell you how much of something you start with, and it'll give you enough information to be able to solve it. But we need to keep track of what's happening. I told you before that every problem is going to involve some K value. It's either going to ask you for the K or it will give you the K and we'll have to figure something else out. ICE in ICE table stands for initial, change, and equilibrium. That's why we call it an ICE table. Again, nothing to do with the ice that we're used to. So when you're given information about an equilibrium reaction and you're asked to solve something about how much of one of the reactants or products you have at the end, we'll have to make one of these. You will make many of these ice tables. I always like to joke at the beginning when we're just starting in chapter 13 with ice tables. Over the next 4 chapters, if I could give you a quarter for every ice table that you do, you would be really happy at the end of this. You would be able to buy yourself something nice. We're going to do a lot of ice tables. Now, it's not that ice tables are dreadful. I'm not giving you, this this evil laugh like, ha, you have to do these ice tables. They're not bad. Nobody dislikes or has a thing about ice tables. They're actually nice because they help us to keep organized. They're a good way to help us to solve problems. So don't be kind of tricked by me talking about it. I'm not trying to make it sound like ice tables are a bad thing, but just know that you'll use them a lot, and don't hesitate to write one out. The couple of seconds that it takes to write an ice table is going to help you to stay very organized, and you'll see every problem I'm going to make an ice table, unless it's something like we just did where we have KC and KP. So this one is referring to handout number 13. Let's go there and see what the problem is. Number 13. At 250, the equilibrium constant Kp for the reaction is 1.8. And so here it is. There's the chemical equation for it, a simple decomposition reaction. Sufficient PCl5, the reactant, is put into a reaction vessel to give an initial pressure of 2.74 atmospheres. Calculate the pressure of PCl5 after the reaction has come to equilibrium. So we're starting, initially, we have a pressure of the reactant, 2.74. The problem says nothing about PCl3 and Cl2. If the problem doesn't refer to those, then you can assume that you're starting with none. I mean, what else are you going to assume? So I have already begun this thing by creating an ice table. Now, for this first problem, I'm writing what the I, the C, and the E stand for. That's the only time that I'll do that. We'll know. But this is the way that we set up the problem. I always give the chemical equation with the K value if it's given to us. And then for the initial, whatever else the problem gives us. The only thing that it tells us is what pressure of the reactant we're starting with. I would contend that we know with certainty this reaction will proceed to the right. It can't not do anything, and it can't go to the left. It can only go to the right. How do I know? What evidence do you have that we are sure it will go to the right with these initial amounts? How can we be positive this thing is going to proceed to the right? So I would even write, oops. I'm going to write because this reaction is reversible. It can go to the right and to the left. I'm saying I know with certainty it's going to go that way. How do you know, Harish? That's one of them, yeah. When you have zero of something, the reaction is always going to shift to make some of it. All equilibrium problems are going to end with some amount of reactant still present and some amount of product still present. You can't end with zero of anything in an equilibrium reaction. You can't end with zero of anything. So if I have zero of something, the reaction is going to shift to make some of it. So that's one reason it's going to go to the right. There's another reason too. What do you see? The K value is greater than 1. That means that this reaction favors the product. So when this thing comes to equilibrium, there will be more products than reactant. Yep. So yeah, for those, we can be sure, based on what we know already about equilibrium, that it's going to go to the right. So that means that this 2.74 atmospheres is going to get smaller. It's going to shift this way. Some of the PCl5 is going to get used up, and therefore its pressure is going to go down. How much does it go down? Well, we don't really know that. So I'm going to have it go down. I'm going to have our change is going to be minus, and I don't know how much it is, so I'm just going to call it X. It's going to go down by some amount, X. And as the PCl5 is getting used up, the products are going to be getting made and increasing their pressure. So over here, the PCl3 is going to go up by X, and the Cl2 will go up by X. Now, all these coefficients are 1s. That does make the problem simple because, like if I have 1 to 2 ratio, then if this goes down by X, that would go up by 2X. So we'll see plenty of examples like that. But for now, down by X, up by X. Another thing that I like to do with an ice table is I will put a box where my final answer is going to be. If you can remember, if not, I'll put it up here. What is the problem even asking for? Calculate the pressure of PCl5 after the system has reached equilibrium. So once the reaction stops, then at the end, what is the pressure of PCl5? So the problem is asking us to find that value. What is the equilibrium pressure of PCl5? Now, I started with 2.74 atmospheres of it. It's going to go down by some amount x. So right now my equilibrium pressure is 2.74 minus x. My products are simple enough. We started with 0 and they went up by x. So at equilibrium, those are both going to be x. And now we have primed ourselves to be able to do some math. I'm going to take that equilibrium line, and you always will just use this. Why? Because the K value, remember, is what the equilibrium ratio of products to reactants is. So you always use that last equilibrium line to do your calculating. So the K is given to us. Kp equals 1.80, which is the product, x times x, that's x squared, divided by the reactant, 2.74 minus x. Solve for x. What do you see? Yeah, we have an x term. An x squared term. That means that we're going to have to use the quadratic formula. That x squared term is not going to reduce or cancel out because this denominator doesn't have both x terms in it. So, yeah, we're stuck with the polynomial. And so it's x squared. That means that we're going to have to use the quadratic formula. If you have a fancy calculator, like Daniel, hold it up high. Daniel. Yeah, one of those TI-84s. Those are so nice. In the math menu, you'll have a polynomial solver. Your math teacher may have even had you program in how to, the quadratic formula. But yeah, if you don't know how to use the solver for polynomials, sometime today, get to know that. We'll do lots of problems that have quadratic formulas. Oh, they told me last hour it was the math. Or is it? You got the math menu and then you go down to numerics? Okay. These older TI-84s, this is an 83, but on the older TI-84s, you'd go to the button that says apps, and it'll be in there. My 83 doesn't have it, so I got to use the formula. Or I'd probably take my phone and just go to Google and type in quadratic solver, and you can find it very easily like that. But yeah, I don't recommend using the quadratic formula, although it's not like having a tooth pulled or whatever. It's not that bad. But yeah, if we can make it easy on ourselves, we all know the quadratic formula. There's even a song that goes with it. So you like to have the song in your head, Notre Dame fight song, then you could actually do the math. Now, can we actually go through mechanically and do this? Is our algebra sharp enough? I'll do this one with you, but from now on, I'm just going to leave it like that and say, you can go for it, figure it out. So, yeah, we have a quantity in the denominator. We're going to multiply that quantity out to get it out of the denominator. So 1.80 times that is going to give us this. I still have it on my calculator. So 1.8 times 2.74 is 4.93. And then minus 1.80x. So I've now distributed that into that quantity, that's those two. And that's equal to x squared. So you take this expression and get everything over on one side, so the whole polynomial equals 0. And I'm going to keep the x squared term positive, so I'll move the other things over. So it's going to be x squared plus 1.80x minus 4.93 equals 0. If you're amazing at factoring, you might be able to factor this thing and then solve for the two roots. Good luck with that. I used to love factoring when the numbers were nice, but when you get decimal numbers in there, no thanks. Okay, so anyway, use the quadratic formula. Now, you know that when you use the quadratic, you get two answers almost every time. The only time you don't is that this number is a perfect, or this expression is a perfect square. Which,
I'm not sure I understand.
Yeah, when you get two answers, listen to this part. one of your two answers you get using the quadratic formula will be physically impossible. You can only use one of the two. One of them is just not viable, and you'll see that. Anybody have the solution to this one? X equals what and x equals what? 1.5. I would say 1.50. And then what's the other solution? Didn't get it yet? Negative 3.29? Yeah, that's right. Negative 3.29. I'm going to give you a moment. Solve it. Make sure that you can get those. I was a little hasty, I guess. No. Why does it only show one?
He's not sure. Like, the teacher shows 1.5, mine shows negative.
Yeah.
I have to do it a different way.
Why would that? Do you? You got the 1.5. What? That's so weird. It's fine. Yeah, you'll get the two roots from a graph. I thought that the solver would make it super simple.
Yeah, not gonna work.
No.
He's not in this one.
Now, with no shame, please, go ahead, ask me whatever you want to ask. If you have a math question, you're not sure how, either I did something here or how to get those two values and you're not getting it, go ahead and ask. Don't feel bad about it. Go ahead, Daniel.
I was just wondering why you had the plus x and plus x when it had the negative x in it.
Yeah, as the reaction goes to the right, the reactants are getting used up, the products are getting made. So the pressure of the reactants is going down as they react away. The products are being formed, so their pressure is going up.
Well, wouldn't that be 2x on the products?
That's going to go up by x, and that's going to go up by x. So this will have a pressure of x at equilibrium, and this will too. So then when we put it into the K expression, you know that the K expression would be the concentration of PCl3 times the concentration of Cl2 over PCl5. It's really the pressure, not the concentration, but two products multiplied together divided by the reactant. So it's x times x divided by 2.74 minus x. So you don't add the two in the K expression, you multiply the two. Okay? Yes? Right. We haven't gotten there yet. We have two values for x. I told you one of them will always be bogus or no good. A negative 3.29 is the one that's no good because you cannot end with anything having a negative pressure or concentration. So if you get a negative, that's the one that is thrown out. Iria? Same process for KC. Yeah, and the next one will have a KC. Yep. And go ahead.
This is ATM, right?
This will be an ATM. Yep. So yeah, when you get an answer for X, 1.5 ATM, I want you to take a look at what the answer choices are. So this was number 13. Number 13, look at how conniving the person writing this was. 13, got that whole question, and then look at choice A, 1.5. Be careful with that. 1.5 is not the correct answer, is it? What did it ask us for? It says calculate the pressure of PCl5 after the system has reached equilibrium. So the PCl5 started at 2.74. We just calculated that it changed. X represents the change in the pressure. So the PCl5 changed by 1.5 atmospheres. The equilibrium pressure of it is 2.74 minus 1.5. That's why I find it very helpful to put a box there. At the end, when you get the answer for X, always take your eyes back up to where that box is and just inspect, do I need to do something else with that x, or is x the answer? In this case, the x answer, the answer is 1.24. I know, it's so easy. And there it is, answer B, 1.24. Anything else about this one? I got two other examples for you today. Let's move on. Number 12 in our examples. Okay, good. Number 12, for the reaction given here, simple reaction, all the coefficients are 1s again. The equilibrium constant is 18.0. It doesn't specify, so that means it's Kc for concentration. If 1 mole of SO2 and 2 moles of NO2 are placed in a 20-liter container, what concentration of SO3 will be present at equilibrium? Into our ice table, only put ATMs for your unit or molarity. This problem, they gave us the amount of the two reactants in moles. Do not put moles into your ice table. Remember that we're given the equilibrium constant. This is Kc. That means at the end, we're going to take the ratio of the products over the reactant concentrations. So don't just put moles into your ice table. We're given the moles, and then it tells us that it's 20-liter container. So if I take you back here, the SO2, it says from the problem, 1 mole was put into that container, and 2 moles were put into that container. Or not that other container, the same container. Remember that the volume, it says, is 20 liters. So when I make my ice table, I am not going to put, that's why I wrote it up above, I'm not going to put 1 mole and 2 moles. When we have a reaction that goes to completion and we need a limiting reactant, we do that. But when we have an ice table, we only leave it in concentration units, or ATM if it's a KP. Like in the last question, it was given an ATM because we were given KP. So if it's KP, use ATM in your ice table. If you're given KC, which it wasn't given, I'll write it in though. K equals 18.0. That's what it said in the problem. So we need to use molarity. 1 mole divided by 20 liters is 0.50 molarity. No, I wrote that wrong. I said it right, but then I wrote it wrong. Thanks, Jason. 0.05 molarity. And then the NO2 is 0.1 molarity. It doesn't say anything about the two products, so we can safely assume that there's 0. Once again, we know for sure this reaction is going to go to the right. It's got to make some products. In fact, it's going to make more products than it'll have reactants at the end. So I know it's going to go this way. Therefore, the SO2 and the NO2 are going to go down. And the SO3 and the NO are going to go up. So that at equilibrium, the SO2 is 0.05 minus X. The NO2 is 0.10 minus X. SO3 is X, and NO is X. Yes?
Did you use moles for the initial because we want to find moles?
No, it doesn't want to find moles. It asks us for the... Yeah, it does ask us what concentration of SO3 will be present. Yeah. So yeah, we're going to have to find the molarity of SO3. And that helps us too, because remember, I was just telling you, I always like, before I even start any calculation, I like to put a box around my quantity that I'm trying to find. So the question is, what is the concentration of SO3 at equilibrium? That's what I'm trying to find. So this time, when we find X, that will be our answer. So let's get at it. We know the K value. We have the concentrations in terms of X, so we're going to do the algebra and solve for X. Kc equals 18.0, and that's equal to x squared, because I got two x terms here, multiply them, x squared, divided by, oh boy, two quantities. 0.05 minus x times 0.10 minus x. Glad it's not me taking this class. You're on your own. Solve for x. You'll get two values. One of them is no good. Decide that too.
Just simple. You just need to put let's put this side in one equation one, this side.
It only works when the polynomials on top and when the denominators on it. Then you can separate it into individual fractions, and then you can see the hooks. But if you get those
It's not bad.
If you have this table using a Troy High School stylus pen, so it's
personally, I'm not.
what?
I think it's no. I think they moved up.
Yeah, there it is. There's our polynomial expression, and that's what we'll put in quadratic or whatever handy solver you have.
Wait, I got a different value this time.
Oh no.
What? Oh, here.
No, dog.
Okay, this is
Yeah. Don't use the graph function. It's not.
I just did.
Yeah.
I did.
Oh, that.
Oh, it's 18 times that gives us just 0.09.
It's not letting me go out.
It's just how it's stuck at the intersection. The random. That's why I got it. It gas. It's a it's a gas.
Well, I guess I can't find detail.
Unless I programmed it wrong. I might
But if you write the
have.
whole equation at once, I think you can't add it up.
That's right.
Because it's y1
Wait, oh, you couldn't get negative concentration.
No zeros.
Yeah, you couldn't get negative concentration.
Did I trip?
It's not that bad. You have a couple.
Can I see your graph?
Did I forget a two-way song?
Wait,
Oh, yeah.
you couldn't get negative concentration, so it has to be.
Do you get two values for it?
Yeah.
X equals 0.048 molarity, and then X also equals, according to the equation, 1.1, or no, 0.11, right? Which one is no good? Which one? No, the smaller one's the answer. The 0.11 is no good.
No, it makes
Why? Yeah?
It makes negative.
Yeah, on the left side, it's 0.05 minus x. So if x is 0.11, I'm going to get a negative concentration. Can't have it. So one of the roots there that you get will always give you some negative value up here. I don't think it'll give you ever something too big, but it'll give you something negative. It should be obvious. The more of these that you do, the more obvious the wrong answer is. So it's 0.048. If I take you back, look at this. B, they give you the answer 0.11. So if you thought it was 0.11, you got all the math right, but then you still got, it's multiple choice, so all that work that you did doesn't matter.
Eliminate everything because it's going to make negative except the 0.048.
Mhm. Anything else about that one? Yeah.
Why isn't it 0.11 again?
Because looking at these two, if you take 0.05 minus 0.11, you're going to get a negative concentration of that. You can't have it.
It's 0.5 minus 0.11.
I've made charging. It's a completely different.
You can't have a negative concentration at equilibrium.
Like when you're graphing, it's not correlated.
Nikhil Smith. The difference between these two, or how to get these two?
Yeah. Okay, I get it now. Okay. That's being done.
The
Yeah.
plugging that in gives you a negative concentration, in
I
which
was
you
putting
can't.
in 0.048, and I was wondering why it was negative.
It's not. Okay. Let's try one more. Yeah, unless anybody has another question about this, don't feel bad asking. We got time. Yeah, go ahead.
Wait, when you do like KC is equal to x squared over 0, do you just always put the products over the reactants?
Products over reactants, always. Yep.
Jason, I think I got this. This is my unit for root.
Okay. Let's try one more for today, and that will be number 17. Seventeen says the brown gas NO2 and the colorless gas N2O4 exist in equilibrium. According to this very simple, small chemical equation. In an experiment, 0.625 moles of N2O4 was introduced into the 5-liter vessel and allowed to decompose until it reached equilibrium. The concentration of N2O4 at equilibrium was 0.075. Calculate Kc for this reaction. Now this one, you're going to see, and that's why tomorrow, almost the entire hour, maybe the entire hour, is just doing examples of problem. We don't even have a new concept tomorrow. It's all just seeing, what do we do in this problem? What do we do in that problem? We're building a repertoire for how do we solve the different kinds of equilibrium problems. For this one, what makes this one different is that we have an empty vessel. There, it says a 5-liter vessel. There it is. Nothing in it until some N2O4 is added to it. So they're adding the product of the reaction to the vessel. It did not add any reactant to the vessel. It did not say anywhere that some NO2 was added to this thing, just the product. So that means this. Now let's remember what we have here. We've got 0.625 moles in a 5-liter vessel. So when I change pages here, I've got my stylus is dying. 0.625 moles in a 5-liter vessel. And that's of N2O4. So when I make an ice table for this, oh boy. Oh geez. All right. No. Now, how do I get rid of those? Okay. So I have my ice table. My N2O4 is put into the vessel. Remember, the question is, what is KC? So we need concentrations in our ice table. Don't just put the 0.6225 moles in there. It's 0.65 divided by 5 is going to give us the concentration, which is 0.125 molarity. Initially, the problem said nothing about the NO2, so that would have to be 0. Now, what I want you to see on this problem is we only start with product in there, and there is no reactant. So the reaction is going to have to go this way. Do not turn the chemical equation around. Never turn the chemical equation around. Whatever you're given and you're asked to come up with a K value for a reaction, use the chemical equation that you're given in the problem. You'll be sorry if you don't. So yeah, I know it's weird as this is, it's going to go backwards. But look at the arrow. It can go backwards or forward. It's a reversible reaction. So it's totally fine if it goes to the left. And that's what it's going to do. This N2O4 is going to go down as the NO2 gets made. I don't have to use any X terms in this problem. If I go back and look at what we're given, it says down here, the N2O4 was introduced in the vessel and allowed to decompose until it reached equilibrium with NO2. The concentration of N2O4 at equilibrium was 0.075. So we don't have this mysterious X that we have to solve for. We know how much it changed. It went from 0.125 molarity down to 0.075 molarity. So we can tell how much it changed by. It went down by 0.05 molarity. I don't have a box on this one because the question is not asking me about any equilibrium concentrations. It's asking me for what the Kc value is. So if we want the Kc value, we need everything in here, which we can easily find from our ice table, because if I know that I used up 0.05 molarity of N2O4, how much NO2 got made? If it went to the left and I used up 0.05 molarity of that, how much of that got made? How much, Uriel? How'd you get it? Right, look at the coefficient ratio. It's a 2-to-1 ratio. So this is the first time that we've seen anything other than a 1 for a coefficient. But if you have a 2-to-1 ratio, then however much this one changes twice as much. So this one is going to go up by 2 times 0.05, which is 0.10. I should be true to my sig figs. This is plus 2 times, here I go again. Okay. Okay. Yeah, I guess I am only stuck with 2 sig figs on this one. So we have our initial, our equilibrium concentrations, and therefore the case, the Kc is products, 0.0750 over reactants, 0.10 squared. So we have to take into account that coefficient twice. Once when we're doing the change, Okay, this NO2 changes by twice as much as the N2O4. And then we also have to account for it when we're doing the K expression. It's got to be raised to that power. So 0.075 divided by 0.1 squared gives us our answer, 7.5. That's it. That's all I got today. Anybody have any questions about anything? So yeah, go ahead, Rishi.
Where did you get that 0.05 the polarity, like 0.05?
That one or that one?
The one on the right.
Okay, so I know that I started with that concentration, and I know from the problem, it told me that I ended with that concentration. So if I started with that and ended with that, it changed by that much. I just subtracted the two. So you know how we have always a multiple choice part that's 16 questions? That's going to be the test. And then when I give you the free response part, it's going to be 4 questions. That will be the quiz.
He's already got it all figured out. He's already went through all the notes. Oh, this guy's actually crazy. I know. This guy will be like, his notes for the hour and he's like, the test. I don't know what kind of like. I was fucking like he's like having fun.